And okay, but of course, when all things back off, let's look at what's the big picture. We're all about entropy right now. Everything we're doing right now is entropy. So we're going to do a lot more entropy today, and then we're going to finish entropy in terms of just developing on it. Okay, so I've introduced this concept as the change in entropy, reversible heat over temperature. I saw online a really good definition of this is you can think of entropy as the ways that heat gets dissipated, the way heat flows through a system, the way heat dilutes through a system, and I kind of like that. It's reversible because it's path independent. Reversible, remember I always thought that was a crock because it's path independent because you chose the path. Whatever, it works. And so therefore, now I'm reviewing from actually a while ago, therefore we can integrate it and do tricks with, I've shown you 2 ways to do this. There's even a couple more. I will show you how to do even one of them today. We can do, again, we can manipulate work, and then we can do temperature. I'm not going to write it down. But now we've already talked about this. This was already on the test. What I talked about last time was S itself. Right? Remember, it has a functional form, and it's the gas constant, R 8.314, divided by Avogadro's number. Sorry, blanking out. And that's because I'm trying to look at single molecules as I'm trying to explain entropy in this form. I want to think about single molecules, and that's why I took the gas constant and divided it by Avogadro's number. If I was talking about a balloon, I would be using R instead of kV. And then we have this number of, this W, which is the number of microstates. And I'm going to do a lot of little tricks with number of microstates to try to get home what it is and make sure that it makes sense, especially with the other stuff that we talked about. And remember, so this is the number of microstates, but it also behaves like a probability. Right, and that's kind of hard to put those two together. And again, I'm going to give a bunch of examples of why that makes sense, and I will have them on the second test. An example that I'll do today, something like it will be on the second test, and there's examples of your homework, so I'm going to help you with your homework today as well. So again, what's really difficult is numbers add, but probabilities don't. That's why this microstate deal is really kind of a pain. Because again, microstates should add, but they don't. Actually, they multiply like a probability. That applies 2 things at once. And I do want you to try to kind of try to forget this, but remember when I tried to, yesterday when I was trying to show you that entropy should be a natural log because of what I just said, I started out with looking at, this as though it was probability, so I was using fractions like flips of a coin. That was really not correct because you really can't have less than 1 microstate. I was doing that because in terms of probability, you're used to fractions, you're used to flips of a coin, and that is how I hopefully showed you that entropy needs to be a natural log. But it was not correct because you can't have fractional microstates. So I always take it a little bit in the knees about how to describe that. Okay, now I've been blabbering about how this is a microstate and a probability, and I have another example other than the little a piece and 3 holes. And what I'm going to do is I'm going to do the same thing, but I'm going to have 2 containers. It's like an Einsteinian thought experiment. And let's divvy this up so there's some kind of magical barrier such that I can add up this entropy. So the one on the left. Okay, again, it's brainless up until I count the microstates. What are they? Same as last Monday. 3, right? Remember, so the X is a molecule, and there's 3 places for it to be. I'm not quite sure how I would build something like that, but nonetheless, and of course, on the right-hand side is exactly the same. Okay, so that's all fine and good. So the total entropy of this thing would be S1 plus S2. So it does add, and that would, of course, it's brainless. I'm just going to say it's 2 times ln 3. Okay, anybody can see that. But now here's where it gets more difficult. I used the extensivity of entropy that it's just like energy because it's a state variable. I should be able to add it up, and I did, and it does work. But I should also be able to work with this formula. I should be able to work with this formula and get the same thing. All right, now this is why this is kind of a pain. All right, so here, let me, to make it even more clear, okay, let me do it this way. Here, I'll write this again for completeness. Okay, what is the total number of microstates? Is it 6? Right? Is it 3 and 3?
0.
It wouldn't be 0. All right? And don't forget these need to be equal, right? Hopefully you see that, right? Obviously, it cannot be 6. So you see that, again, this is why this is a pain. Here's how you actually resolve that. If this is here, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. See? Here, there's 3 options because of this guy. If this was here, there were 3 more. And if this was here, there's 3 more. There was 9. There was 9 total microstates. Right? And remember that A ln B is ln B to the A. Right? So 2 ln 3 is ln 3 squared, which is ln 9. Right? It works. So anyway, and again, a bunch of more examples because I'm going to throw this at the test. What I did last time is actually kind of a funky question, and I used to actually get it wrong for a couple of years. Let's just do this one. And I'll just remind you that I just wrote this down. Let's add a player as though a chemical reaction occurred. And this guy's kind of funky because, what is this? Is this 6? You remember? It's still 3, right. Right, so this is an unusual problem. Now this one's obvious, right? 1, 2, 3. Now remember, this one is actually 1, 2, 3, right? Commute them. And remember that you can't distinguish them. So you can't do this here and here, right? No, do not do this. All right, so because the x's are the same. Okay, now this is kind of a funky one because it looks like if this was a reaction, this x like split into 2 x's, I normally would have thought that you would have actually increased entropy, and I'm going to show you that that is the case, except for this weird chessboard, which is very unrealistically small. All right, what happens is, and again, I'm really embarrassed. I've gone 10 years actually getting this example wrong. I would expect entropy to increase because I've added more players, right? Again, it's extensive, and I've thrown more stuff in. It seems like I should have added some entropy, but I've lost volume, right? Less places. So they actually counterbalance. I doubled the number of players, but I have the free volume. And so that ended up negating. That's why the entropies are the same. Okay, just wanted to point that out. And I probably should stop this example. But let's do an example more like what's on your homework. So I'm going to have you figure out changes of entropy for a chemical reaction. And of course, we're gonna make the chemical reaction really simple. And so I've got a box with 4 compartments. And if I'm going to do a chemical reaction, I'm going to have a molecule, but it's going to be like a diatomic. So it's going to be like O2 or something like that, right? So we got to figure out this entropy, and this will be a unimolecular decomposition reaction, which when you go to grad school, you start in physical chemistry, you start learning about unimolecular decompositions, because if you can't get that right, you can't really do anything. And for the heck of it, I'll just put them in these boxes right now. And this will be SI, this will be SF, and of course delta S, which is the thing that I really care about, is going to be SF minus SI by definition, final minus initial. And tell you what, let me go ahead and write this down here. KBLN, that's a given. Okay, what is it? Remember, this molecule is stuck together. There's only one molecule. You're going to write 4, right? Instead of 3 holes, there's 4, and this is simple. Okay, let me give you this one because because I had to look it up on Wikipedia. It turns out that the first molecule has n number of boxes, so you might want to write down n as the number of boxes, so it's 4. And the second molecule has n minus 1 number of boxes. Again, these are the number, I had to look up how to do permutations, which you all had in math class at some point. I had it in high school. And it's kind of neat, but it's also really a pain. Then you divide by 2, and that's again because I can't distinguish between the two x's. The two molecules are the same. And to convince you of that, let's see, this is, by the way, then let's see, 4 times 3 over 2 is 2 times 3, this is 6. Okay. Now, the point of this, so it's 6. Now, again, this one's brainless. There's 4 boxes for it to be in. There's 4 microstates. There's 6. Let me show you. 1, 2, 3, 4, 5, 6. Right, you see? It's easy, right? So, and I hope that these questions are actually kind of fun. So they're free points, right? Now, remember, I did not do 1, 2. I did not do that. No, that's why I have this right here, because that doesn't technically count. And yes, if this was like NO, and then this was an N and that was an O, that 2 would have to go away. That's actually correct, by the way. But it's not, it's O2. So you do got to think about those things. And you can measure them and they're real. So anyway, okay, so I've got KB, LM, 6 minus KB, LM, 4. And so that's, the main thing is that it's positive. Okay. That's really all I wanted to show you is that, yeah, I mean, it makes sense. We always tell you, and you're going to get a heaping dose of this, if this doesn't quite, if you don't quite remember this, or maybe you weren't shown this, but gas, when the reactions produce a lot of gas, it tends to be very favored. Those reactions tend to occur. That's actually like burning gasoline. You turn octane gas, it's vaporized before, I know it's a liquid, but it's vaporized before it blows up. And you get tons of CO2 and H2O out of it, and it's hot. And that's a very, you know that that's a favorable reaction. Of course, it goes like a gunshot, right? And that's one of the reasons is because it produces a lot of gas, which is entropically favored. And we just talked about the second law, more entropy is more spontaneous. So that's definitely going to work. Okay, now let me actually state that a different way for you, Mark. That hopefully was logical. Let me do it more mathematically. Again, you know that entropy increases in a spontaneous reaction. Spontaneous means, yes, that happens, that goes. So that's looking like that's very favorable. It isn't 100% certain. I'm going to jump ahead a little bit to what I'm going to get to at the end of the day. I'll kind of introduce this right now. I want to remind you about this little dandy that you had in high school and as a freshman. And it looks, again, I'm able to define delta S, thinking about molecules, again, with this very simple, a molecule splits in 2. I can't really do much better than, that's the simplest one I can come up with. Now that I've got delta S defined, actually I want to not muddle that by multiplying it by minus T. So I want to get delta S on its own, right? Now again, I've defined this guy, and this is the entropy change of the system because there's no other little subscripts here. It's not total, it's not surroundings, this is the system. So, in terms of is this reaction, if someone showed me this reaction and said, okay, O2 splits in 2, is that thermodynamically favored? Or especially maybe if I didn't even know if it was O2, it's just a molecule splits in 2, is that thermodynamically favored? I have to say maybe. Right? If someone had to say, what's your educated guess? My guess is yes, but I can't say absolutely because I don't know enough about the outside change in entropy. So again, the interior entropy has increased, and I've proven that, but is the reaction spontaneous? I have to know the outside entropy. In other words, how much heat had to go into the system to break the bonds, and that input of energy represents a loss of entropy on the outside. All right, it's a little bit much, wasn't it? But anyway, okay, let me just say it again slowly. I see entropy increasing on the inside, but there has to be a loss of entropy on the outside because I had to input some heat to do it, right? That makes sense. I am actually seeing that here. Again, entropy on the inside is positive, but does that make it spontaneous? Again, it has to be balanced by the entropy of the outside. Where's that? There's the entropy change. Remember, that's a heat exchange. Remember that in this example, I'm putting heat in, and that's in heat over temperature. Heat over temperature is entropy. So where's the entropy change in the outside? You've got one of two choices. Delta H, right. Remember, you were taught that delta H was whether something is exothermic or endothermic. That's the change in heat, right? Remember, we said under constant pressure that delta H is heat. So entropy change of the system plus entropy change of the outside. So this is actually total entropy. Now, what was the rule you were taught in high school? Delta G is always what for a spontaneous reaction?
Negative.
Okay, now isn't that confusing? Because Monday I said, a spontaneous reaction is dictated by a total entropy change that's positive. I never said delta G was negative. Now, that's kind of messed up. Again, you were taught delta G is negative for a reaction to be spontaneous, but I overwrote that on Monday. You didn't even question it. I overwrote that and I said, no, total entropy change is positive. Okay, now hold on a second. If this is total entropy change, which has to be positive, and delta G was negative, 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 positive. You see, they're the same thing. If delta G is negative, then total entropy is positive. Right? That's what we were actually showing you, but we thought that since you were 18, you're just too stupid to understand. So that's actually true. But anyway, I'm going to actually prove this today. There's more to this than meets the eye. I'm just trying to get you to, baby steps, right? Last bit, and then I'm going to drop this jazz, is I want to connect back to this thing that I've already proven to you, that thing on top, LMDF over VI, and also understand a little bit more about what are microstates really. Let's do gas in a box, because you can't, again, do much more simple. And again, I'm sorry there's not much biochemistry here. I can't really help that because I don't want to start talking about the entropy of DNA if you can't do gas in a box, right? Okay, the box is empty, the entropy is what? How many ways can this box be empty? How many microstates? Right, it's just one, so this is 0. That's because the box is there, so it has entropy. It's just that there's only one way for that box to be a box, I guess. Nothing's going on inside of it. Okay, so now I add a molecule, just one. And now here's the thing. I hate to do this because this is formally not correct, but I think it makes sense to say that the number of microstates is actually the volume. Because if you think about it, and this is a bit of an aside, I don't want you to... Now, I know that this is wrong, by the way, because I can't feed a natural log something with units, so this cannot be correct, but it is very instructional. So let's make the volume very, very small. And before it was empty and there was no entropy, now I'm going to fill that. The box was really small, only enough to fit a molecule and just barely. What would be the entropy of that? I think it'd still be 1, well, sorry, not 1, it'd be 0. The number of microstates would still be 1 because the volume barely fits the molecule. So again, nothing's happening. So in this case, I would think that the entropy is still 0. But when this box expands, this thing can bounce around like mad. And that's, I think, my definition of entropy. So this is why I think, although not formally correct because I have a unit problem, it does make sense to me that I can relate number of microstates has got to be at least a function of volume, even though I'm not totally sure what that is. Okay, now, if you've really kind of gotten this, you're going to be able to do this one. I've now got 2 molecules. Is it 2V? What's the microstates? 2V? Notice I've drawn a fraction. Is it 2V though?
V minus 1?
Not be just V squared. -1 would be such a small volume that it wouldn't really count, right? So you're thinking about the volume minus the volume left over. That would actually be the same number because molecules are so small, right? So that was good thinking. And then, of course, the molecules are the same. Okay. So, and again, now I can't emphasize this isn't really correct, but it does get you to think about this the right way. And so if I keep doing this with more and more molecules, what I find is that the absolute entropy would be ln g to dx. Oh, I'm sorry, over n. Let me make sure that's correct. Is that? Yeah, I think that's. Is that right? I think I might have made some kind of, oh yeah, that's right. Okay, so, all right, now what I want to do, I think I might have made some kind of stupid mistake here. What I want to do is figure out what this is. So now remember that the thing that's kind of a biz knocker about these derivatives, as much as this seems like, oh yeah, hopefully you're used to this now, so you're not too scared. But remember, this isn't P, which would be equal to nRT over V. It's now KL in number of microstates, and how that number of microstates depends on volume can be kind of horribly complicated. In this case, it's not terrible because I've simplified it. Okay, let's see what we get. So we're going to get the KB can come out because it's a constant. And what I've got is the derivative of the natural log of Vn over n. That might be n factorial. Anyway. Okay, and so then what I get, I can bring out the n. So I got KBn. And then I would just divide that by V. Yeah. Yeah, right, right. Because this is actually ln VVN minus ln n, 1 over n. No, it's minus ln n, and that term goes away. Anyway, just do this on the website. I don't want to bog down with this. And then what I want to do is just point out, so this is correct. I want to point out that n again is the number of molecules times, let's say it was like a mole, so it'd be 6.022 times 10 to the 23, and this is R divided by 6.022 times 10 to the 23. I think those numbers cancel. Anyway, so we can make this nR over V. So again, remember, Kb is the gas constant for a molecule, but I have a mole of molecules. Just by it works mathematically and by logic that this is true. Okay, and something that actually a lot of you did wrong on the test, by the way, you had to do derivatives, but you integrated instead. Not a lot I can do for you, sorry, but here's when you should have done that. So I've got the changing up of the change in V is nR over V. So you bring over the change in V, you integrate them, and now you've got delta S, sorry, that's a big therefore, is nR ln dF over VI. I'll toss this up in a second, but yeah, there you go. Okay, my point being here, here, let me toss this up so you can see the whole thing, that I got this idea that entropy, it's not the change in entropy, entropy is a natural log of microstates. For gases, it makes sense to me that it's like the number of microstates is volume, but that can't be quite right, but we're going to roll with it anyway. I then use the probabilistic viewpoint of microstates when I say that for n molecules it's PVN over n because they're indistinguishable. Again, don't worry so much about that. I'm not going to put that on the test or anything. And that leads me to derive delta S as nR ln dF over VI, which is right here too. Right. Now notice I didn't get the CV ln temperature bit because I didn't change temperature. If I didn't allow it to happen, then of course that part's not there. Okay? You're all right? Okay, a little bored? All right, anyway, look, remember that this is a graduate level concept. I'm actually going to spend an hour with grad students today where we're going to calculate the chemical potential or Fermi energy of a metal doing this. It's a little bit more complicated. Baby steps, right? So this, if you do go to grad school, you will see this. It's not that bad, especially if we think about chess pieces on a chessboard, which is on your homework. And a chess piece is going to have a baby. And so you're going to calculate the change in entropy of that reaction, and you're going to find it's favored. And you're even going to think about whether it's favored under adiabatic or isothermal conditions. It's really not hard. It's only a couple points because it's been set up to be easy. So if you go to grad school, it does get harder, but you're not in grad school. So anyway, okay, so that's that for KBLNW. Again, I will have it on the second test, maybe as an extra credit question. I hope you found it interesting, but whatever. Okay, now I want to explain why you're all going to die. Oh, I'm sorry, that's kind of dramatic. Sorry. I want to explain why the universe is doomed. It's true, the universe is doomed. I'm about to explain why. This is why everything happens. This is actually the most important part of the entire class. I could actually stop this class after today. I actually think a lot about game theory. What if you all paid me to stop the class after today? Would you do it? Now I have to assign, here's the trick. You pay me, I'll stop the class. But I have to assign a grade. The grade will be a C. Would you still do it? No, isn't that funny? See, I'm through the class. I don't have to worry about it. So anyway, it's all about me. Okay, this is why everything happens. And this guy Clausius gets all the credit. You probably never heard of him, right? I never heard of him before this class. This guy is kind of more important than Einstein because this explains why the sun's going to rise, why you're going to die. Why the universe turns to hydrogen? Yeah, sorry, I know, it's awful. Why the universe is going to turn into a cold bath of hydrogen gas. Not even H2, just H. That's all that's going to be left. The universe will end that way, and this is what says that it's going to happen, Clausius Inequality. Again, this is why everything happens. Well, I want to start with the change in U, which of course is heat and work. And because I can do this path independent, whether I'm doing adiabatic reversible, adiabatic irreversible, isothermal, I'm going to follow the reversible path because it's just easier to prove my point. I could do this by an irreversible path, except it will just take me more derivational steps, so why would I do that? So I'm going to do the change in U, and I choose the reversible path. I didn't have to, it's just easier to do it this way. Okay, so I'm also going to choose an isothermal path. So here, I'll put this right here. So I'm going to follow isothermal and reversible path, and therefore, you know that the change, let me get this right, the change in heat is going to be minus the change in work. Okay, now change in work, we've been doing a lot with this, and you know that the difference between reversible and irreversible was on the exam. I introduced this, it seems like it was a while ago, wasn't it? By the way, this homework set's the 5th one. There's only 10 homework sets. We're halfway through. Yeah, not bad. Okay, so, it seems like a while ago, doesn't it? When we were doing irreversible, you saw that it was this area, and reversible was this area, and again, that's because the P versus V curve is bigger because of this slow let go of the magic piston. So that kept the pressure on the exterior. What have I done? That kept the exterior pressure a little high just because I did that. And you know that the reversible work, because of the minus sign, right? Reversible work is always the most negative. And so let me put that down mathematically. And then let me get you, in case you get a little hung up with these minus signs. I hate greater than and less than signs, by the way. I always get twisted up by them. Let me do this. Okay, again, just to remind you about reversible, irreversible work. We did it with this graph. It's brainlessly obvious that the reversible work is always the most negative, and therefore I can write this. And then part of that second homework that hopefully it didn't seem like you guys got too caught up on that. But remember that when I say reversible work is the most negative, it's also to say that it doesn't mean it's always negative, right? It just means it's less than irreversible work, right? It's always less than. To say that reversible work is the most negative work is to say that it's simply less than irreversible work. And remember that the reason I'm saying that and the reason you do know it is because you had to do the case of compressions, which are positive work, right? You had to do that. You had to do this graph for a compression, and you saw that reversible work was still the most negative, even if the work is positive. It's just less than. Okay, yeah, on that one. All right. This is less than that, and the big number minus the small number is always positive. All right. So that's again 5th grade mathematics for you. I just don't like greater than less than signs. It tends to mess me up. Okay, so now you know this and you know this, and so therefore I can make this stipulation that anything that happens with work, the opposite happens with heat, which is true. So what I'm going to do is I'm going to write the same thing down, except that I have to switch the reversible and the not reversible and just do that. So again, yeah, I mean, it's the same thing. It's just, the reason I do it this way, go from here, remind you of this and go there, is because this is really easy to know. I mean, this again, you've done this a long time ago. This is really not hard. You just have to kind of accept that, well, yeah, down this path, they're opposite. So yeah, it does work. And by the way, this does show you, remember I was telling you about, well, again, reversible and irreversible work is very easy to understand. Heat is a bit like, what does it mean to be reversibly heated versus irreversibly? It means that the magic cylinder and the Bic lighter I used to light it, to warm it up, it means that all the heat goes into it because if I didn't do it reversibly, some would have been lost. Right, you can see that, how if more heat goes in, that's a bigger number. Then heat was lost, and that's actually how you do reversible versus irreversible. That's how you think about reversible versus irreversible heating. Anyway, so I'm really having a bad one right now. Hopefully you're okay with this. This is, this isn't quite the Clausius Inequality. This is the Clausius Inequality. Remember that I am going down a isothermal reversible path, although this works for any path because I'm talking about state variables. Again, this is just a blank, easy way to do this. Because I'm isothermal, the temperature is well defined. So I'm going to divide by temperature. Nothing happens. This is what I hate about inequalities, is that when you start multiplying things, I get confused. Anyway, so I can divide by the temperature, and therefore now you know this. Right, by definition. And this is actually the Clausius inequality, right here. And, ooh, I should have had units, by the way. You know, I'm a stickler for units, so. Okay, and then you die. And this proves it. This actually proves everything. This proves why you woke up this morning, it proves why you're going to die, why the universe runs of hydrogen, why my cat is annoying and just keeps, like, she grabs the twist ties for the bread, she grabs it and she sees me. Sorry, I'm talking about my cat. This is why everything happens right here. It's just a little hard to see. So now I've already gone over this a couple of times. Now I've done a derivation. It was started with this graph. Don't forget this. Start with this graph, decided on a path, divide by t, yada, yada, yada. So if anything, if you're a derivational type of person, I have not made any mistakes. Like, I really couldn't have. It's too easy. Does it make sense? Now remember that, okay, let's do equal to 0. That would be when the process is reversible, right? So if the heat transaction was reversible, in whatever it is, the cat compresses the cylinder, whatever, the cat runs off with the twist tie. If the cat runs off with the twist tie reversibly, then the heat's reversible, and then these cancel, and that's 0. Now, so that makes sense. Oh, also, if you're adiabatic, then remember this is greater than 0, and this subtracts off. If you're adiabatic, there's nothing here, right? So this can't, for half the conditions, this can't even contribute. Anyway, this kind of makes sense, right? This again, it's a derivation, which I didn't make any mistakes, and hopefully it just kind of makes sense in general, like I'm kind of trying to develop that, but not doing such a great job. But now let's put another face to it. Again, entropy of the system, and what? You already know, I mean, I've already told it to you like twice. Entropy of the surroundings, right. This is actually the total. This is actually a proof of the second law. This is why I told you that this is the most important thing ever. Technically, this is a proof of the second law. And don't forget, we did it with a graph. I always thought that was, this graph is why you're going to die. I didn't tell you that so you wouldn't hate it. But it is true. This is a proof that entropy always increases. And that dictates why everything that will happen is going to happen. And that's, again, because, now this, again, is brainless. This is exactly what I said it is, the entropy change of the inside. And this is the entropy change of the outside. And I've actually done it several times now, but it bears repeating one more time. The surroundings is only affected, we're going to simplify the magic cylinder and my cat with the twist tie. The exterior universe is only affected by a heat transaction. And whatever happens to the system, which is the change in Q, the exterior changes by minus Q. So what happens on the inside times -1 is what happens on the outside. Right there. The negatives are opposites. And so that hopefully makes sense. and divide by T, you've got entropy by definition. Okay, so what? And so, again, entropy always increases. Now, that's all fine and good, but what I want to do is start putting a little face on it. Actually, let me start with the new board. And, because this is a little complicated, and this is a derivation you have to do on your homework. So this is a simple version of the one that you're going to do on your homework, which is a little bit harder. I'm going to actually start back a step and do the change in S by change in heat over temperature is greater than or equal to 0. Let me just not put the units down for a second. If we're at constant volume, then what I'm trying to do is whittle in more thermodynamic variables into this, because right now this is a bit of a pain. You'll see when I get to the end. I kind of know the end. Okay, if volume is constant, then tell me what the heat is. Give me something else for heat, something easier than trying to figure out whether I efficiently use my big lighter to heat up the magic cylinder. Give me a different letter. Again, I stipulated constant volume for a reason. This I'm going to leave alone. Heat. Change in U. Right, remember, change in U is change in heat, change in work, but there's no change in work because I'm at constant volume. Okay. I've done that. Now what I'm going to do is multiply times minus T. And so now what I've got is change in U minus T, change in S. Now again, I hate greater than less than. You have to flip it. If 5 is greater than 0, minus 5 is less than 0. If you get confused, that's how you do it. Get it out of your head. Okay, so I've got that. And now, let me make another stipulation. Let's say that there's no entropy change. And this would be an adiabatic reversible process, by the way. Remember, you don't need to know this for this. It's just I want to remind you what we talked about last time. Entropy changes, all the entropy change on adiabatic reversible are all 0. Just to remind you. Anyway, you can have a process that is adiabatic and reversible, and therefore the entropy change is 0. In which case, the change in U is less than or equal to 0. And that'd be joules, but anyway. Huh? So there you go, right? Again, this is why you're dead. Yeah. Think you're kind of like, so what? Kind of like, so what? Again, does this kind of look familiar? Changing U minus T delta S kind of sound familiar? You just don't have delta G, right? And you don't have delta H. But it certainly looks right, doesn't it? Okay, so what's happening is that you're looking at this thinking, okay, yeah, this is a derivation, I follow it, but so what? So what is that? It never really changed. It's still total entropy, right? I started with total entropy, and I've ended with a total entropy. I've just muddled with it a bit with algebra and multiplying it. So I've messed up the units. But anyway, let me again state that I am still dealing with total entropy. This is still total entropy. Technically, it's been multiplied by minus T. So this is the total entropy times minus T. And so what this is really saying is that if U goes down, total entropy goes up. You see, this is still a definition for spontaneous. Again, the total entropy is still in this equation. It's still here, and the total entropy is the most important thing you could ever know because it's going to kill you, right? And the universe is going to die because of total entropy, and it's in here. Right, so again, total entropy increases if U goes down, but under certain stipulations. Constant volume and constant entropy. So for a process at constant volume that's technically adiabatic and reversible, if you want to know whether the process is spontaneous, you don't want the change in G, you want the change in U. Now remember, we told you that delta G was negative means something is spontaneous. I just convinced you that that's actually total entropy increasing is spontaneous until delta G was just hiding that fact. And now I just belied that. Now I'm telling you it's change in U. Right? So again, change in G was negative. No, change in S total is positive. changing G was just standing in for that, and now I'm saying that, even that's wrong, now I'm saying it's a change of U. And I am saying that, by the way. The trick is to notice what I held constant. I held volume constant and I held entropy constant. Now, when you did organic chemistry, did you do things at constant volume? Your reactions, it was in a beaker. Is that a constant volume or constant pressure? Remember we've done constant pressure, right. If anyone ever tells you to do a chemical reaction in an enclosed volume, say no, because those explode, right? Even in chemistry and in nature, we do not like to do things at constant volume. We tend to do them at constant pressure. Okay, if I did this at constant pressure, all of this would have changed. The way it would have changed is that I would have had enthalpy. Right? Because now enthalpy is heat. And what I would have ended up with is the change in H minus T delta S is less than or equal to 0. And at constant entropy, delta H is negative. All right? At constant pressure, like the reactions you did. Okay, now again, the reaction was done in a beaker, and you probably did it in an ice bath. Constant entropy or constant temperature? Constant temperature. Right, oil bath, ice bath. Constant temperature. Yeah, I know it's maybe warming or getting cold or whatever, but over the time scale that the reaction occurs, like from atom standpoint, it was at constant temperature. Okay, so notice that delta H is negative is constant pressure, constant entropy. Now, did you ever do a reaction at constant entropy? All right, so again, you've done it at constant temperature, constant pressure. Did you ever do constant pressure, constant entropy? Did you ever do that? Did you ever add an entropy regulator to your organic chemical reaction? No. Do you know what one looks like? An entropy regulator? It looks like a magic fish with a top hat. And if you look at it, it looks back at you. And no, they don't exist. There's no such thing as an entropy regulator. There is a temperature regulator. Humanity has never figured out how to build an entropy regulator. They don't exist. We do, however, very easily have temperature regulators. Now, here's what I'm going to tell you, and I have to return your homework. What do you think I'm going to derive if I make a stipulation? It's not constant pressure, constant pressure, but instead of constant entropy, what if I made it constant temperature? What do you think I'm going to derive here? We haven't covered it yet, but it's what letter? G, right. Constant pressure, constant temperature. What we're going to derive next time is delta G is negative. The thing that we told you was absolutely true, but wasn't. It depended on what you held constant. It's just that this world is a constant pressure, constant temperature world. That's why we told you that, because it was just the easiest lie. Anyway.